All right, here's try it 2.13. Man, they really make you work for this one. They say, look at the graph in figure 2.35, this picture right here, and ask you to figure out all sorts of stuff. First of all, the y-intercept. Well, the y-intercept is where you cross the y-axis. This is the y-axis right here. And I want the y-intercept of j of t. So j of t is this guy in orange, and it appears to cross the y-axis right here. Is this height 5? It is 5. It's exactly 5. From a graph, you can't really tell. Maybe it's 5.1. Maybe it's 5.01. But I know it's exactly 5 because I know the equation of that function. And you could rewrite this as negative 1t plus 5. So the y-intercept is exactly 5. But I don't think you were asked to look at this algebraically. You were asked to do it more geometrically. So you'd say the y-intercept appears to be about 5 and call that good. Y-intercept. If you want to write it as a point, some teachers get picky about this kind of stuff, some don't. So when the x-coordinate is 0 and the y-coordinate is 5. X-intercept or intercepts. Well, let's take a look at that same function in orange. The x-intercept is where it crosses the x-axis. The x-axis is this guy right here. So it crossed the x-axis right here. Coincidentally, also at 5. I get 5 comma 0. You could figure that out algebraically by using this equation given up here. Note that if t equals 5, if I put 5 into this machine, 5 minus 5 is 0. When 5 goes in, 0 comes out. When 5 goes in, 0 comes out, this point right here. The slope, okay, I can figure that out. To figure out the slope, find any 2 points on the line. And I mean, you could do it algebraically. You could say it's y2 minus y1 over x2 minus x1. If I was calling this x1 and y1 and this x2 and y2, I could do it that way and use this formula. Maybe it's easier to just kind of count. From this point to this point, how far do you go up? Well, I go up by negative 5 because I go down 5. Okay, how far do you go to the right? I go to the right by 5. Okay, so you go up by negative 5 and you go right by 5. So the slope is negative 5/5, aka negative 1. So the slope, I'll use the letter m to represent it as negative 1. Question, these guys parallel? Are they perpendicular? Are they neither? Well, they sure as hell ain't parallel because they don't look parallel to me. Parallel means they have the same slope. They'd be running kind of side by side. Certainly not parallel. The way you could figure that out is by going back up here and kind of looking at the two slopes. What about perpendicular? They're not perpendicular, although it looks kind of close. To be perpendicular, the line in blue would have to look more like this. So they don't look perpendicular. They don't cross at a T, I guess. That's one way you could argue that. You could figure this out more algebraically. You could say that the slope of the line in blue is not the negative reciprocal of the slope of the line in orange. Because the slope of the line in orange is negative 1. And the negative reciprocal of negative 1 is positive 1. Because the negative part of the negative reciprocal changes the sign. And the reciprocal flips the fraction upside down. So the fraction 1 over 1 flipped upside down is 1 over 1, which is still 1. So if these two lines were perpendicular, the slope of the line in blue would have to be exactly 1. And it's not. I mean, the slope equaling 1 is this diagonal line, not this one in blue right here. So neither. Is j of t an increasing, decreasing function, or neither? Well, j of t, again, this one in orange right here. You can figure that out. I think the way your book kind of defines things is it says if the slope is positive, it's increasing. If the slope is negative, it's decreasing. So since the slope is negative 1, it's decreasing. The way I like to talk through it is if you're walking left to right, are you going up or are you going down? You start out over here and you got to get over here, you're going downhill, right? So it's decreasing. This thing is decreasing. Write a transformation description for j of t from the identity. Good Lord. Okay, so if you started out with the graph f of x equals x, this diagonal line, poorly drawn diagonal line right here. I don't know if that's any better. I don't know why I care so much. It goes through that point, this point. I think I got that right. If you start out with this line right here, how could you get to the thing in green? Well, a couple ways you could look at this. I think the easiest way would be to look at this guy. I'm just making things uglier. I'm going to use my version here, negative t plus 5. So I know that j of t is negative t plus 5. This dotted green line right here would be f of t equals t. So how do I get from here to here? Well, I do two things. First of all, I multiply all the heights by -1. Your book would say you reflect things over the x-axis, but I prefer to not think about transformations as that type, and instead I say that all the old heights get multiplied by -1. So this height was 0, 0 times -1, still 0. This height was 1, 1 times -1 is -1. This height was 2, 2 times -1 is -1. You end up with the graph that looks something like this. And you're like, but wait a minute, that's not what you want. Right, I've only taken care of this part right here. I still have to add 5. You add 5 to each of these heights, and it'll bring you right up here to this orange line. So how do you describe all that? I would describe it by saying first multiply old heights by -1. Then, what did I do? Add 3 to all heights. That's the way it makes sense in my mind. That's the way I talk through function transformations. Other people, your book, for example, would argue that what you really did is you first reflected your graph over the x-axis, and maybe that's even worth writing. Multiply old heights by -1, aka reflect over the x-axis. So this first, the stuff before the comma could also be written as this. And then add 3 to the heights, shift up by 3. Think about it either way. This is easier to describe to somebody, but I think this, if you think about it this way, makes it easier to actually apply the transformations, especially when transformations get much more complicated than the ones here. We'll call that good.